Hello all, welcome back to Climate Dynamics. Today our lecture is the Wind-Driven Circulation Part 1. The reading for this section is Marshall and Plum Chapter 10. In this section we're going to define wind stress, ocean eddy, wind-driven circulation, thermohaline circulation, and surface wind stress. The questions we're going to answer are, what are the major drivers of ocean temperatures? What are the major drivers of ocean salinity? How important are ocean eddies to the circulation of the ocean? How does surface wind stress drive oceanic currents? Why is mass transport in the ocean at a 90-degree angle to the wind stress? We're going to start off by talking about the drivers of oceanic temperature and salinity. Here's a global plot of sea surface temperatures. You've already seen this to date in one of our earlier lectures where we talked about the character of the ocean. So what are the primary drivers of these temperatures? Well, they're primarily driven by 5 factors. The most obvious factor, and perhaps the most dominant, is surface warming. That is, solar radiation that's able to make it through the atmosphere warms the oceanic surface directly. This then results in the equator to pole heat gradients that we've seen in the ocean and those that match that of the atmosphere. However, there are other drivers of oceanic temperatures that are also important. We've talked about some of these factors already when talking about the interactions between the ocean and the atmosphere. A prominent one is surface cooling. Namely, the ocean itself is also in a state of energetic balance. That is, the amount of energy it receives must be equal to the amount of energy it emits in order for the temperature of the ocean to stay constant. So it must have a mechanism by which the ocean cools naturally. The primary mechanism is through surface cooling, that is, outgoing long-wave fluxes and sensible heat loss. That is, both through radiative forcing, by naturally emitting radiation away from the surface, but also through sensible heat loss. So as the ocean interacts with the atmosphere, it'll be transferring some of that heat to the atmosphere as well. And this leads to the atmosphere maintaining relatively constant temperatures when it's over the ocean. This is one of the main drivers for why near coastal regions typically have more modest temperature changes compared to more inland locations. Namely, the oceans provide a moderator to those near-surface atmospheric temperatures, allowing temperatures to remain roughly constant. The third primary driver of oceanic temperatures is evaporative cooling. This is essentially latent heat flux. That is, as ocean waters evaporate, we have a cooling of the liquid ocean. That is, the most energetic molecules within the ocean naturally leave the surface during the process of evaporation, leaving behind cooler oceanic water molecules. The fourth major driver is meridional currents. That is, there is circulations in the ocean that we've already discussed that are responsible for moving around ocean waters. This is effectively advection or convection drivers of heat transport. Meridional currents are responsible for a strong poleward transport of warm oceanic waters along the western edge of ocean basins. We'll study today why the oceans naturally give rise to these strong western boundary currents. As well, they're also associated with a general bulk equatorial transport through the interior of the ocean. That is, through the central part of the ocean, all the way through the eastern edge or the eastern edge of the ocean basin, we have generally equatorward transport of ocean waters. Finally, in the vertical, there is processes by which oceanic waters can be exchanged. This is known as either upwelling or downwelling. Upwelling is common particularly along the eastern edges of ocean basins or along the western coasts of continents. This is responsible then for the vertical exchange of ocean waters, especially in these coastal regions. Here's a map of surface salinity, showing higher saline regions in warmer colors and less saline regions in cooler colors. Notice the most saline regions of the ocean are located in the mid-latitudes, with lower salinities located near the poles, as well as lower salinities located over the equatorial band, in particular over the maritime continent. There are some exceptions, of course, to this distribution. For instance, we see a very saline Mediterranean Sea, as well as less saline interior lakes and seas. Ocean salinity is primarily driven by 4 factors. 1, evaporation. Namely, as fresh water evaporates from the ocean surface, it leaves behind salt. That salt then leads to a higher density of salt in the ocean waters, hence driving up the local salinity. The amount of evaporation that occurs is closely related to the amount of solar radiation reaching the Earth's surface. Namely, if we were to look at a map of highest insolation, you'll recall that From our earlier discussion, this insolation is typically maximized in these mid-latitudinal regions, which tend to have clear skies, as well as being relatively close to the equatorial band. Consequently, evaporation is high in the subtropics. Precipitation is the opposite driver. Namely, as precipitation occurs, fresh water is injected into the local ocean. This then results in a decrease in the density of salt within the ocean water, hence driving down the local salinity. The third driver is river runoff. River runoff has two contributions to salinity. Over long time periods, it provides a mechanism by which weathered terrain can transport nutrients and salts into the ocean. However, over short time periods, most rivers are associated with fresh water. Hence, this freshwater injection into the oceans results in typically low saline regions of ocean next to the largest mouths of these continental rivers. The fourth mechanism is through brine rejection, which is a common mechanism that occurs in the polar regions. As seawater solidifies, that is, as the liquid turns into ice, it rejects salt in the process. That is, the fresh water turns into ice, but leaving salt behind. Consequently, the formation of sea ice pulls fresh water from the ocean, driving up the concentration of salts in the local ocean waters. Consequently, when sea ice is forming, the liquid ocean tends to become more saline. In order to show the correlation between ocean salinity and precipitation and evaporation, we show two plots here. The top plot shows the surface practical salinity, with warmer colors representing more saline regions. The bottom plot shows precipitation minus evaporation, with warmer colors corresponding to more precipitation and cooler colors corresponding to more evaporation. What you'll notice is that there's a strong correlation between P minus E and surface practical salinity. That is, in regions where precipitation is high, we typically have low surface practical salinity. Along this equatorial band, which corresponds to the intertropical convergence zone, we have a convergence of winds from the northern and southern hemispheres, leading to an increase in local precipitation. This local precipitation then drives up the injection of fresh water into these regions, and consequently drives down the salinity density as well in the oceans. In the subtropics regions, where we see more evaporation than precipitation, we see increases in salinity in the oceans. This is because fresh water is being drawn from the oceans, and hence it leaves behind more saline water. You'll notice that in terms of a moisture budget, we have a net export of moisture that must occur in these subtropical regions. In fact, we see more evaporation in these regions than precipitation, and the water is then exported towards the equator in order to fuel the precipitation that occurs along this band. Since more precipitation occurs than evaporation along the ITCZ, it must have an alternative source of moisture. In particular, it draws that moisture from these subtropical regions. In the polar regions, we see modest levels of precipitation minus evaporation. These are very dry regions generally, and the decrease in salinity through these regions is driven by other factors. All right, let's talk about ocean eddies. Here's a map that we showed earlier about the large-scale oceanic currents that occur in the major ocean basins of the world. These are the subtropical gyres associated with large-scale circulations. In the northern hemisphere, they're associated with clockwise motion, and in the southern hemisphere, associated with counterclockwise motion. This large-scale mean flow hides some of the nuanced character that is actually present within the oceans. So far, we've primarily described the oceanic circulation in terms of annual means or climatologies. But there's far more nuance that occurs on finer scales, particularly finer temporal and finer spatial scales. This is usually captured in the form of ocean eddies, which are prominent features of the ocean, induced by instabilities from horizontal shears in the flow. Formally defined, an ocean eddy is a circular current of water. These eddies emerge naturally from ocean currents that are pinched off and produce relatively local circulations of radii approximately 100 kilometers. You can see some of these features very clearly in the Gulf Stream of the sea surface temperature plots that we've looked at previously. Look in particular for small circular circulations that occur within these plots. They are essentially little pockets of warmer temperatures that have split off from the warmer current to the south and are floating in cooler waters to the north. They can also be enhanced by looking at instantaneous current speeds. On the left-hand plot here from the U.S. Department of Energy E3SM, we see clear circular enhanced regions, little donuts per se, of high-speed circulation. These local circular features are very prominent throughout the ocean and look to be particularly prominent in some of the faster-moving oceanic regions, particularly along the Gulf Stream. When we have a high-speed current circulation, such as the Gulf Stream, moving adjacent to slower-moving ocean waters, what is known as a Kelvin-Helmholtz instability can give rise to circular motions that then get pinched off from the central circulation. Consequently, we get the formation of these ocean eddies, these sustained circular features that tend to drift off through the ocean. You can also see them on the right-hand side, showing concurrent ocean temperatures. Again, these little circular features essentially provide a means for warm ocean waters to be basically isolated within the colder surrounding ocean waters. These ocean eddies have many sizes associated with them, but a typical size is on the order of 100 to 200 kilometers. Here's another shot from the NASA Perpetual Ocean. You may want to go back and watch the YouTube video of the Perpetual Ocean to see some of these eddies in action. Again, in the maritime continent region, we see very prominent circulations associated with these ocean eddies. You'll also notice that the relative current velocities associated with these eddies are pretty comparable to the large-scale average current speeds. Hence, this mean view of the oceanic circulation does mask some of these more finer scale behaviors that occur on shorter time and space scales. In order to assess how well these two features compare, that is, the mean circulation and the perturbation from that circulation associated with shorter in time and shorter in space circulations, we can use a Reynolds average decomposition type approach of, for instance, sea surface height. Namely, if we take the sea surface height in terms of its spatial and temporal coordinates and break it up into a time mean plus a perturbation, we can then calculate the standard deviation of the surface height about the time mean as the square root of the square of that perturbed component taken as an average over the region. By doing so, we obtain the following two figures. On the top right, we see the mean current velocity, that is the average instantaneous ocean current velocity in each location. Typical ocean currents are relatively weak, but in some of these regions we do see much higher mean current velocities, reaching between 20 and 40 centimeters per second. The bottom plot shows the average standard deviation from that mean current velocity. That is, in regions with standard deviation that matches that of the mean current velocity, oceanic eddies will typically have circulations that are approximately of the same magnitude as the mean current velocity. Thus, the ocean eddies in these regions, where the standard deviation is similar to the mean, can even oppose the mean current flow. The main conclusion that you want to get from this, then, is that the standard deviation tends to be on the same order of magnitude as the mean current velocity. So these eddies can actually be quite prominent relative to the mean flow, and consequently looking at only the mean flow hides quite a bit of detail about the large-scale global circulation. These figures lead us to conclude that the ocean is not really steady and laminar, but is really highly turbulent, and is in a constant state of turbulence, even though it's responsible for basically a large-scale transport of oceanic waters along these oceanic gyres. It nonetheless also has some finer scale features associated with it that are quite prominent. Again, I'll refer you back to look at the NASA Perpetual Ocean video in order to get a feel of really how prominent these ocean eddies are, and how looking at purely the mean is a bit misleading. Oceanic eddies, on the scale of about 100 kilometers radius, and with lifetimes of months, are much different than their atmospheric counterparts. Namely, in the atmosphere, these type of eddies that naturally arise from the circulation are associated with instabilities in the polar jet and the mid-latitudinal jet stream. They are then known as extratropical cyclones. They have large-scale circulation associated with them on the order of 1,000 to 10,000 kilometers, and typically have lifetimes of days. Again, these extratropical cyclones or large-scale circulations are then responsible for bringing large-scale weather systems through the mid-latitudes. All right, So let's move on to talking about the wind-driven circulation, and in particular, how wind stress plays a role in the oceanic Ekman layers. Recall our discussion of the ocean temperature structure. In the near surface of the ocean, we have a relatively warm, well-mixed layer. This area is well mixed because of wind-driven turbulence that occurs within the mixed layer. Essentially, this region is fairly homogeneous because of continuous mixing that occurs throughout these depths. However, since the ocean is also fairly stably stratified, we also have that below this mixed layer, the ocean tends to remain in basically a constant stratification. Through this region, we have a quick decline in temperature as you go to deeper depths. Namely, as the oceanic waters get farther and farther from the surface, they are exposed to less radiation as well as exposed to less of the water from the mixed layer. So there's less opportunity for temperature mixing to occur. In the abyss, in the deepest part of the open ocean, below 4,000 meters depth, the region is in complete darkness and is essentially thermodynamically homogeneous. Looking at the meridional vertical structure of the ocean essentially consists of basically a warm, salty, stratified lens of fluid that is located near the surface. Below that is the drop in temperature, known as the thermocline, that separates the surface layer from the interior ocean. And then at depth, it has a relatively well-mixed abyss with very weak mean flow. The ocean circulations that we've seen to date are largely driven by two factors. One is the wind-driven circulation, which refers to tangential stresses at the ocean surface due to the prevailing wind systems. That is, the winds that continuously blow across the surface induce friction on the ocean, which then can induce circulation. The second driver is the thermohaline circulation, which is a global circulation driven by convection at polar latitudes. This circulation will be studied more in the next lecture when we talk about the global exchange of oceanic waters. Geostrophic currents that we have discussed to date are driven by horizontal gradients in the density field. These horizontal gradients in the density field are induced by Ekman pumping and suction. That is, it's induced by vertical motions that occur because of near-surface friction. This near-surface friction is induced by the wind-driven circulation. Let's study this in a bit more quantitative detail. By definition, the surface wind stress is the force on the ocean surface induced by friction at the atmosphere-ocean interface. Wind stress is closely connected to near-surface turbulence, as well as oceanic turbulence, including wave heights. Consequently, it's typical to use empirical relationships in order to assess how much force is actually induced on the ocean surface because of a wind stress. A common method is via the bulk formula, which connects these gradients in wind speed to induced forces. Here we see a typical bulk formula. The stress induced on the oceanic surface is proportional to the density of the air, a bulk transfer coefficient, the wind magnitude at 10 meters altitude, as well as the wind magnitude at the surface. The product of all of these terms then gives the estimate for the wind stress. The bulk transfer coefficients are typically derived empirically and can depend on local conditions. Here we see a plot of surface wind stresses experienced by the ocean. Colors indicate the magnitude of the wind stress, and the vector indicates the direction. You'll notice that the surface wind stresses vectors shown here are very close to the near-surface wind speed vectors. Namely, we see a convergence of winds towards the intertropical convergence zone. We see a strong Antarctic circumpolar circulation, as well as mid-latitudinal westerlies. Typical wind stresses are on the order of 0.02 newtons per meter squared, but can get as high as 0.2 newtons per meter squared in some of the regions where winds tend to be the strongest. Alright, so let's study what happens in the oceanic Ekman layer. We discussed this already in the case of the atmospheric Ekman layer, but recall from subgeostrophic flow that we essentially have a balance between three terms, namely pressure gradient, Coriolis, and friction. What is friction in this case? Well, the friction is the applied body force due to the action of the wind on the ocean. So we'll need to account for that wind stress in this friction term. To calculate the total amount of force experienced by fluid parcels within the Ekman layer, we note that we have an induced stress that is occurring at the atmosphere-ocean interface, and through turbulent action that is carried down through the region of the Ekman layer. The stress is applied then within this elemental slab of fluid depth delta. The Ekman stress diminishes quickly with depth, and so approximating it as only applying within this layer is reasonable. To calculate the total force applied, we calculate force per unit area divided by mass per unit area, by taking the differences between the incurred stress at the top of the layer minus the incurred stress at the bottom, and dividing that by rho reference times delta z, we get a formula for the frictional force induced as 1 over rho reference times di tau di z. A similar formula applies in the y direction. With frictional force in hand, we then have a 3-term balance for each of the meridional and zonal velocities. Namely, on the top we have Coriolis force, pressure gradient, and frictional force for the zonal momentum equation, and similarly in the second equation for the meridional momentum equation. To solve for the actual circulation, we need to know the distribution of wind stress through the Ekman layer. The stress at the surface is of course known. This is the wind stress calculated from the bulk formula. From observations, the direct influence of wind forcing decays with depth really rapidly, namely in a few tens of meters. So at the bottom of the Ekman layer, effectively the stress induced by the wind is equal to 0. Typical values associated with the Ekman layer then are on the order of 10 to 100 meters. Note that this is a much thinner region than the mixed layer of the ocean. Okay, let's delve into this formula in a little bit more detail and try to understand what is happening in the Ekman layer. As mentioned before, our two equations describing the motion of fluid within this Ekman layer is given in the top left here. Our first action is to split this wind into geostrophic and ageostrophic parts. Remember that the geostrophic component is associated with balance between Coriolis and pressure gradient forces, and the ageostrophic wind comes in as the additional wind on top of the geostrophic wind. If we plug this into the formula above, that allows us to eliminate the geostrophic wind from the balance, and what we then obtain is a formula associating the ageostrophic wind with the frictional force on the fluid parcel. Specifically, we have F K cross U ageostrophic is equal to 1 over rho reference times the z derivative of the vector wind stress. We're going to multiply this equation through by rho reference and integrate over the depth of the Ekman layer. This then gives us a formula for the mass transport in the Ekman layer, which is, more specifically, the integral over the depth of the Ekman layer of rho reference times the ageostrophic velocity. You might recall that this looks like a flux term. That is, it's the transport associated with the ageostrophic flow. If we then take this equation and cross it again with k, and use the relationship k cross m Ekman equals negative m Ekman, we then obtain an expression for m Ekman in terms of the wind stress and the Coriolis parameter. Specifically, m Ekman is equal to tau wind cross k divided by the Coriolis parameter. Qualitatively, this means that the direction of mass transport must be at a 90-degree angle to the induced wind stress. Specifically, in the northern hemisphere, mass transport is 90 degrees to the right of the wind stress. In the southern hemisphere, the mass transport is 90 degrees to the left. What this implies is that the current velocity, that is, the oceanic movement in the near surface, must be slightly biased to the right of the induced wind stress in the northern hemisphere in order to support this direction of mass transport. Further, through the Ekman layer, we must have that the current velocity rotates in a clockwise direction in the northern hemisphere. The direction of rotation is the opposite in the southern hemisphere. This rotation with depth then supports this direction of mass transport. This result might be quite surprising, namely, in this case of a geophysical flow where Coriolis force is relevant. What we are seeing is that the wind is not inducing a current flow which is aligned with the actual wind direction. Instead, the current flow is slightly misaligned. Let's look at this quantitatively. Okay, let's go back to our understanding of how viscosity behaves through the Ekman layer. To do so, we're going to go back really early in Introduction to Atmospheric Dynamics where we discussed viscosity and how viscosity enters into the Navier-Stokes equations. A brief review is as follows. Consider two fluid parcels stacked on top of each other. These two fluid parcels have a difference of velocities. The top fluid parcel travels at velocity u sub t, and the bottom fluid parcel travels at velocity u. Because of contact being made along the surface of these fluid parcels, they induce a frictional force in the flow direction. The shear stress is then going to be proportional to the difference in velocities and inversely proportional to the separation. That is, we have tau sub x is proportional to ut minus u all over delta z. Introducing a proportionality constant here, namely k times rho reference, we then have tau x is approximately equal to k rho reference di u di z in the limit of small delta z. Okay, since we know that the wind stress is going to be given by k rho reference di u di z, and that the frictional force is going to be given by 1 over rho reference times di tau x di z, we can plug this into our equations of motion and obtain this coupled formula for the wind velocities, incorporating Coriolis force, pressure gradient force, and frictional forces. This is the balanced law that must then be maintained within the Ekman layer. Using the geostrophic wind relationship, we can replace the pressure gradient with the geostrophic wind velocities, hence arriving at the final form below. In order to close these equations prior to their solution, we need to have an expression for the geostrophic wind. We're going to assume that the geostrophic wind doesn't vary much through the Ekman layer. This then allows us to substitute in the expansion of the real wind in terms of geostrophic and ageostrophic components, and hence obtain a set of two coupled differential equations for u ageostrophic and v ageostrophic. Okay, let's try to solve these equations. We've got two coupled second-order constant coefficient partial differential equations. If we take the second derivative of the top equation and substitute in the second equation, we'll obtain a single partial differential equation in terms of the dependent quantity uag. This is a fourth-order constant coefficient partial differential equation. Thus, the solutions are e to the ax, where we can solve for the coefficient a. The boundary conditions that arise from the physical system are as follows. The first boundary condition is that at the top of the Ekman layer, namely at the atmosphere-ocean interface, we have that the imposed stress is the same as the wind stress. So tau 0 is equal to tau wind. This then requires that the vertical derivative of the ageostrophic wind must be equal to tau wind over k rho reference, in accordance with our earlier discussion about wind stress. Note that this boundary condition is not a condition on the ageostrophic wind itself, but is instead a condition on the vertical derivative of the ageostrophic wind. If it were a no-slip condition, that is, if the ageostrophic wind was imposed directly, that would require that the current velocity be aligned with the wind, but that is not the case here. The second boundary condition that we will have for these equations is that the solutions are bounded. Namely, as we go towards infinite depth at the bottom, as z goes towards negative infinity, we must have that the ageostrophic wind goes to 0. This is simply because in the interior of the ocean, we know that the wind is very closely approximated by the geostrophic wind, and so the ageostrophic wind must disappear. This will also lead to us having no growing solutions, and will eliminate two of the possible solutions that arise from solving the differential equation. Okay, so solving this directly and imposing boundary conditions leads to a more general solution. We'll consider a special case of that solution here, where we consider a purely zonal wind stress, because this will give us a little bit more intuition into the problem. So with this solution, the imposed condition at the top is that tau wind x over k rho reference is equal to u over delta. Recall that this term on the left-hand side of the equal sign has units of meters per second per meter. Specifically, it's a difference in a velocity over a particular depth. So here we're saying that the velocity imposition varies by about capital U over the depth of the Ekman layer. The second equation is that tau wind y is equal to 0. That is, there is no meridional wind stress imposed. Under these conditions, we can solve directly for the ageostrophic wind in the zonal and meridional directions and obtain the equations below. This expression may be quite daunting at first look, but let's consider the special case of the near surface. In the near surface, that is, imposing z equals 0, we have that the ageostrophic wind in the zonal direction is u over 2 delta gamma, and the ageostrophic wind in the meridional direction is negative u over 2 delta gamma. The sign of the ageostrophic wind in the meridional direction depends on the hemisphere, In the northern hemisphere, the wind is directed slightly to the south, and in the southern hemisphere, the wind is directed slightly to the north, thus matching the figure on the right-hand side here. You'll notice also that the magnitude of the zonal and meridional components are the same. This means that the surface current must be directed at a 45-degree angle to the imposed wind stress. Repeating the solution of these differential equations with different wind directions produces analogous results. The surface current will always be directed 45 degrees to the right of the wind stress in the northern hemisphere, and similarly in the southern hemisphere but to the left. This also means that the current is directed 45 degrees to the left of the mass transport in the northern hemisphere. What we observe in examining the solution as we go from z equals 0 to depth is that the current velocity rotates clockwise as the ageostrophic velocity goes to 0. The decay of the ageostrophic velocity is approximately exponential with depth. Okay, let's return to the surface wind stress map with our new knowledge in hand. Again, recall that the surface wind stress is directed in the same direction as the near-surface flow. As wind converges towards the intertropical convergence zone, we're also going to have flow that is roughly easterly. That is because the wind is being turned by the Coriolis force as it moves towards the equator. In the subtropics region, so approximately 15 degrees north to 30 degrees north, we have wind vectors that are directed from the northeast towards the southwest. If you recall that the ocean currents are then directed approximately 45 degrees to the right of that, we will have ocean currents that then come from the east and move towards the west, thus supporting the flow of the ocean gyres. Farther north than that, in the North Pacific Ocean, we see flow that is slightly directed from southwest to northeast. Again, if the flow is approximately to the right of that direction of induced wind stress, then we will have ocean currents that move from west to east. You'll notice this pattern of wind stress is consistent regardless of which ocean basin you're in. In the southern hemisphere, this logic is reversed. But in general, we see this consistency that then shows up between the atmospheric induced wind stress and the ocean current directions. All right, that's all for today. Thank you very much for joining me. Next time we'll finish off our discussion of the wind-driven circulation.